They will gain electrons. And why is that?
Because we're close. But they only need like a couple.
To gain stability is better for them to gain electrons than to lose them, right? So for 1s2, 2s2, 2p6, 3s2, 3p5. So you are already 3p5. You get one electron, form an anion, and negatively charged, and gain stability. The same is true for all these 17 group, and that's why you call it 17. And for all these, you just like elements in the 17th group will form a uni-negative, like one negative anions. Okay, 16 minus 2s, right? Minus 2s. Nitrogen group minus 3s. Carbon plus 4 minus 4, both. Because it's equally likely for them to lose or gain electrons. Okay, so you have plus 4 and minus 4. So organic chemistry, when I'll touch upon a little bit about this, in a little bit in bonding and a little bit in organic geochemistry when we reach there. Okay. This is also metal, but we come into a type of element which is called a metalloid, which is not exactly metal or not exactly metal, non-metal. It somewhere stays in the middle. So we get some of these metalloids in the D block. So boron is a non-metal. Gallium, germanium, these are metalloids. There are more. Which?
Selenium one?
Selenium?
Oh, I'm sorry. I said
tin. Tin is a metal. Maybe indium, I don't know. Thallium, maybe, I don't know. This is gallium, this is germanium. So these two definitely. Okay. Silicon. Okay. So the metals on the left side in the S blocks, the non-metals somewhere in here, in this range. And there are some metals, and definitely these are all metals. So we will look into how the general nature of elements change. Where do you find more metallic elements? Where do you find more non-metallic elements in periodic table and periodic properties? But for now, let's think like this. Like anything that loses electron and forms a cation generally has a metallic behavior. Generally. And the opposite goes for the nonmetals. Anything that accepts an electron kind of has like a non-metallic property. Okay? Now, coming back to Tiffany's question. Can you remind me of the question? I forgot. You had some. Right. So copper is in the D block because the last electron, as you saw, was coming in into the D orbital. So this is called the inner transition. Sorry, this is called the transition metals. So most of the D blocks are transition, so they are metals and they are in this middle zone, and that's why they are called transition. You can also think about transition as going from like a metallic to a non-metallic in that region. So it's called a transition metals. In here, this is called inner transition. And we have two groups. So this is called inner transition. Does anyone know the names of these two inner transitions? Right, so you have lanthanides and actinides. So the elements, 14 elements following lanthanum and actinium form a set of really interesting elements called the lanthanides and the actinides. This will become really important when we study trace element or the rare earth element geochemistry. Because these elements or these inner transition metals that are there, or inner transition elements that are there, are very small in number. But so when they're very small in number, they generally do not form a metal like an ore of their own. So for example, copper, which is here, will form a copper ore. Iron will form an iron ore. Lead will form a lead ore, because that's another huge industry of like extraction of metals from their ores. Okay, in these, the inner transition or the rare earths, which are extremely important in the electronics industry, so we are trying to find out more resources from which you can actually extract these rare earth elements, because we need these rare earth elements in technology. So if you need it in your cars, you need it in your any kind of like electronic circuits. I don't know exactly how they use it, but I know that these elements, these lanthanides, actinides, the inner transitions are required to build electronic items. Now, we do not see that a downsurge in demand of electronic items, but the supply could be inhibited or at least thwarted by the lack of these rare earths. Now, since these are rare earths, you do not find them in huge quantities. Yes?
I was going to ask, to that end, do you know, like historically, I don't know, like during the medieval and Renaissance times, whenever they found these kinds of like copper, iron ores, and I mean, presumably the trace elements were in there, do you think that they might have kind of just thrown them in the trash, not knowing that they were there? Or, I mean, because you mentioned that they're used for electronics. Do you think that they were kind of like neglected in the past?
You don't even have to go back that far. Like even if you go back 100 years ago, maybe there are so many things that we do not know now, and we might be doing like, or if we do not know if an essential element exists, of course I'll be throwing them out, right? Yeah. At one point of time, so, and the reverse is also true. Sometimes things were really expensive before, like aluminium. Right. I don't know when, but if you go back, go back in history, kings and like royal people were eating in aluminium plates because aluminium was very expensive, because we did not know the correct procedure to extract aluminium from its ore. So it was very expensive. And that's why the royalty were using expensive items, aluminium. And then we found out a way to extract aluminium, and aluminium became cheap. So the reverse could also be happening, right? There might be, you're right, like there might be so many things that people might have just thrown because we didn't know.
The problem is like when we, like I'm in rare earth for my master's, we're finding parts per trillion. I mean, like it's so minuscule that even when they were smelting copper back in the day, they didn't know what they had. Right. So there was no possible way for them to think about the lanthanides when they only could fathom up to like calcium. Right. Okay. So, but I mean, even studying the rare earth, there's only maybe 5 places in the U.S. that have done full workups. It's really just an untouched area of geoscience that's burgeoning, but the technology is just now getting to the point where it's affordable to actually run samples. Okay. Because I think I can name of 4 universities in all the U.S. that really have the capability to do rare earth and trace element at an affordable, like under $50 a sample. Right. And I mean, as he's saying, 50 years from now, they'll probably have drones that can go over and through spectroscopy be able to tell what's there. But right now, it's just nothing. I see. Okay.
So on Moon, we have a region called the creep terrain, and it's potassium, rare earth elements, and phosphorus concentrated. Right now, we just know that there is some concentration of these creep material in the creep terrains on Moon. But we do not exactly know, like Brian said, how much is the concentration. So there might be a technology that might come up in which we can fly a drone or an orbiter to exactly measure the concentration of this creep material on Moon. So if we can go there, if there is a huge amount of creep, we can go there and actually mine that. So that is in situ research utilization that NASA is trying to do. But right now it's all like, a lot has to be done before we get there. Okay? But in the inner transition elements and the rare earth elements become really important because they can act as tracers of important geochemical processes. How can they behave as tracers? Because these can substitute elements in minerals like plagioclase or olivine. So the major minerals that are there on Earth, they are made up of iron and magnesium and calcium silicon oxide. So basically, these are all the oxides, right? So the silicates, the phyllosilicates, the ionosilicates, all these kinds of different rock-forming minerals are there. And these things can become a part of those rock-forming minerals through substitution, and we'll see that. And based on the concentration or the relative concentrations of the different inner transition elements, if we map that, we can find out a lot about how these major elements or the major minerals formed. It's a really cool technique. We'll learn about those when we are looking into the rare earth element or trace geochemistry. Okay? So the general idea is you have the S block, alkali metals, alkaline earths, P block, the transition metals. Most of these things are metals. Okay, then you have and how many columns are here?
12. Well, actually, 10. Sorry.
10. So how was Hunter able to tell it was 10 so quickly? He didn't count.
The
Go
difference
from
between the
2 to
groups.
13.
D has 10.
The number of
Max,
rooms.
max.
Oh, yeah, these people are smart.
D has 10. And what's the number here?
14.
14, right? So 2 for each electron coming into S, 6 for each electron coming in P's, 10 for D's, and 14 for the F's. It makes sense. It's just the number of electrons coming in, okay? So copper still is in the D block, and it is more likely, it is more favorable for copper to form a cation than an anion, okay? So now if you have copper plus, or you don't know if, can you tell me what are the cationic forms of copper that might exist?
2 plus.
Iron has 2 cations, Fe2 plus and Fe3 plus. There are many which form 2 different kinds of cations. Copper is one of them. Think why copper would have that. And how do you think about that? How do you start thinking about these kinds of problems? By starting to write the electronic configuration. So write the electronic configuration and think for a moment. Why or what are the oxidized forms of copper? Or you can think about it and we can discuss it in the next class. So to start with the electronic configuration and go from there.
Copper is problem number 29.
Yes. Okay. +1 is correct. Because it's 4s1, 3d10, so it will just remove 1.
Because it's partially filled, so you take from your 4s to make it.
Oh, so you have 4s1 and 3d10, right? Although this was filled completely, but you start taking out from the 4s because it's the outermost, it's the 4. So you start taking out from here. So for example, scandium, which is 21. So this is 4s2, 3d1. It's not just that. I mean, I'm not writing the ones that follow. That are already written, okay? So when you form scandium plus, what will be the electronic configuration?
Everything.
4s2.
4s2.
Where will the electron be coming out from?
The deep orbital.
No,
Oh no, because in this higher, right?
it's 4. Electrons are coming out of this, not this. Because it is 4. Although 4s got filled first, but it will be vacated. Although this 3d one was the last one to get the electron, but it will not lose electron going out first because 4s is like the outer one that is already there.
So, if it loses out of the 4, right?
So this becomes 4s1.
What would happen to the 3D1? Because now it's.
What do you think? Good question. Is this stable?
Less.
And that is why scandium will do this. And this will vacate everything. This is the more stable form of scandium. Yeah, I mean, electronic configuration is really interesting. You can find a lot of answers to your questions just by doing electronic configuration. Okay? We can spend a lot of time here, but I would ask you to think about questions and come up with those questions and we can discuss it. Okay? So you understood the Hund's rule of maximum multiplicity. It's just that the electrons are going to individual boxes first before forming pairs. Okay? Now, I've written this thing about Pauli's exclusion principle, but first let's think about the quantum number. So we already have discussed 2 quantum numbers before. They were what? What were the quantum numbers?
N.
Yeah, and what was it is n, but what do we call that?
The principal quantity.
Principal quantum number, right? Represented by n, and this gives you information about the what? Size. So the bigger the n is, the bigger the size of any orbital. Any orbital, it can be S or P or D or F, whatever. It's just the size. Also, when we were looking at the groups in the periodic table, they were giving you information about the outermost electrons, like the valence electrons. What does the periods give you information about?
They are like the.
Essentially, yes.
Number of orbits.
Maximum number of orbits, and that's the size, right? So the groups and the periods, they give you specific information about a specific element. Just by looking into the electronic configuration, you can now place, I can give you any element and you will be able to place it in the period just by knowing what's the maximum number of electrons that are there, right? So if we did lead, what was the maximum n associated with it? Go back to your notes. What was the maximum n? So we wrote the electronic configuration.
6.
6? I mean, I don't know. I mean, if it's 6, it's 6.
What was the question again?
What's the maximum N associated with lead?
I agree.
6? Okay. I think it's 6. And what's the valence number of electrons? 4. I know this. I don't know this, but I know this. I can find this out because I know the 14th group is this. So this is period 2, 3, 4, 5, 6. And it's in the 4 because it's in the 14th group. Now, D will also have, so in here you also have a similar electronic configuration, and in similar, by similar I mean you will also have a few which will have 4 electrons in the outermost shell, in here as well, in the D. Okay? And in previous times we used to call them 2A and 2B, 1A and 1B, 4A, 4B. So if this would be 4B, this would be 4A and things like that. But we made it all simple. So in here, when you go from group 1, 2, 3, this becomes 3. Because scandium is 21, so this is 4s1, 4s2, 3d1, right? So 3 electrons, kind of. That's the connotation in here. But it's 1, 2, 3, 4 because in the D you have 1. Okay? There is some value in memorizing stuff. Not always. I do not always tell people to memorize, but there is some value. In here, I can quickly tell you which period it is just by, I don't know the number, atomic number, but I can find out because I know this is 6, this is 14. I can add just the number of just the number of elements that come between this and this. Because between this and this, how many were filled? So only S and P were getting filled between this and this.
S2, P6.
Right?
8.
In here, no. Just think about it. When you're going from this and this, when you're going here. So let's say you hit a carbon. This was 6. How many electrons have to be filled in before you reach here? 8. So you can quickly say that this, whatever that thing is 14. Confused? Not clear? So there is a fixed, now, okay. Periods. Period 1 has 2 elements. How many elements does period 2 has? How many elements? Period 2, 8. And where is that 8 coming from?
It's a maximum number of electrons that can fill the S and P orbitals.
The S and the P. So when you're going from here, there are 2 in here, and there are 6 that are getting filled in.
So to go from like group 3 to 4, you would add like 18.
Yes. It should, so if you add 18, 32, check if it's 32. I can tell you it's 32 because, see again, memorizing. I know the people who will be working with this is 21, this is 30, 31, 32. How did you get 18? Courtney, why did you add 18? Why not 8?
Because when you get that big, it could take 18.
Because then there was an additional D block that was getting filled in. That's why. In the first, only 2 were there. First period only had 2 because only S was getting filled. Because 1 has only 1 S. There is no 1 P or 1 D. So period 1 will only have 2 elements because each goes here and here. So period 1 has 2 elements just by filling in the S. Tiffany, you're going to ask something? Okay. 2. Now what are the, so you have 2S and 2P. So how many elements in period 2? 8. 3? 18. And that's why you added, right? That's why you added. Because in helium, this, you knew this was 2. You knew that 6 elements were getting added, so this becomes 6 plus 2, 8. You again know 10 are, I'm missing something.
18.
This becomes 18 because 10 are getting added. And this becomes 36 because 18 are getting added. Okay, so it should make sense when you're adding. So each period will only have a set number of electrons and therefore the set number of elements that are getting filled in. So the periods are giving you information about the maximum size. So 1, so 3, 3p, 3d, things like that. Because you're increasing the size when you're going from 1 to 2 to 3, n gives you information about the size. Now, we were talking about lead. Let's go back to lead. The maximum n that was associated with this was 6, right? Right? Okay, so what's the n for that last electron? What's the principal quantum number for that electron? So what was it was 6, I can tell you, 6p4 was the electronic configuration, isn't it? Now I did not memorize it, I just knew because I knew 6 and I knew it's in the 14 and it's in the p block, so it should be p and it's in the 14th group, so 4 electrons must be coming in. So it should be 6p4, okay? Now, the principal quantum number, did that make sense that I did not memorize this and got it because it made sense? So this is the last electron that is coming in. So this electron will have a principal quantum number associated with that electron. So what's the principal quantum number associated with that electron?
Still 6.
It's 6, right? So the n associated with that number is n. The next will go